Welcome back to the video lecture series for Introduction to Data Programming using Scala. In this video, we're continuing on talking about recursion. We're talking about graphs, but now instead of just looking at the easier question of reachability, we want to try to calculate the shortest path. So remember, our graph is a set of vertices along with a set of edges that connect these vertices, possibly directed. And so what I want to be able to do in this video is write a function that when I give it a starting vertex and an ending vertex, it will return to me the sum of the weights across the shortest path, the smallest sum of those weights. So in this case, in order to go from 0 to 3, there are a number of paths. I could go through the path labeled 2 and then to 4. I could go 2, 5, 2, or I could go 3, 2. Clearly this bottom one is the lowest sum of the weights, and so we want to write an algorithm that will find that. Now, the code for doing this, I'll go ahead and delete that comment, is going to be in many ways very similar to can-reach. So I'm actually going to start with that, and then we'll edit it. Shortest path takes a current location along with a destination and the graph. We're going to pass in our visited, and we'll talk about that a little bit more in just a bit, but we still have this issue that we don't want to be able to go back and forth between two vertices. That shouldn't be allowed. And instead of returning a Boolean now, this is going to return whatever the sum of our weights would be. In this case, our weights are integers, so this is going to return that. Notice this is not returning the path. It is only returning the sum of the weights on the lowest cost path. And the reason for that is that there could be multiple paths that are tied. In fact, the number of paths that could be connecting them is exponential. So we're just going to return one value here so that we don't have to worry about the ambiguities incurred there. So if you're at your destination, what is the cost of getting to your destination? It's not true. Now it's 0. And we have this loop going through. Previously our return value had been a Boolean. We'll have to think about what our return value is here. Our return value needs to be equal to this loop is going to go through and find every possible path from where we are to the end. And it's going to give us the length of each of those paths. So I want to return the shortest of those different values. I think I'm actually going to do this. I'm going to get rid of the ret. I'm going to create a new variable called path lengths, and I'm going to use the same for loop, but now I'm going to yield a value from this for loop. So if I haven't visited someplace and the graph has an edge that goes from there, what I want to yield is the result of my recursive call, shortest path, from that location to the destination, but I need to add on to that the cost of getting to I from my current location. So I take the weight in the graph from the current location to I, and I add that to the shortest path from I to the destination. And then what I'm going to return here is the minimum value of those path lengths. And what are we not happy about? What type are we inferring here? An any val. Oh, that would do it. How about I put this if right there so that we only yield things that have connections. There we go. The problem that I had before was an if that has no else is, has to have the ability to return a unit type. So I was getting an any val because it could be unit or it could be the integer that I wanted. by putting this if up here instead of inside of the loop, the yield will only yield values when there is a connection, and that gives me what I want. There's a problem with this piece of code, but maybe we should uncover it by running this. Shortest path from 0, I believe I was going to 3, and I'm pretty sure that the graph that we have here is still that. Looks like it. So on the graph 2, and we're going to start off with a whole bunch of false values in our visited array. False and 5. I actually found the smallest value for me. I'm going to have to think about how to uncover this particular error. In order to make it so that because there is an error in the code, but I need to make it so the graph will demonstrate that. So I'm going to take this 2 here and make it a 7, and then make this 5 a 1, and I'm going to make this a 7 as well. Okay, so the connection from 0 to 1, from 0, oh hey, this is a somewhat different graph here. I replaced that with a 0. From 0 to 1 is a 7. The connection from 2 to 3 is a 7. And actually I didn't want this to be a 1. I'm perfectly happy with that still being a 5. What I was going to do is introduce another edge going from here to here, so from 2 back to 1, that is a 1. Obviously this is not some type of like road system, because if you can get from 1 to 2 with 5, it's probably not possible even 2 to 1 with 5, but there are other types of graphs that do not have to be symmetric. And now so on this modified graph, remember there's an extra edge for a 1 here that I haven't drawn in. I should be able to get there in 8 that way. This route is 11, this route is 19, and this route is 10. So the 8 is what should win. It goes from 0 to 2 to 1 to 3. And if we run this, it does not find a path of 8. Notice that it's not even close. It finds a path of 19. Can we go from 7? I'm surprised it didn't find an 11 for us the way this is written right now. Let's make sure that so 0 to 1 is 7, and 1 to 3 is of length 4. But first it would have gone that particular route, and the way that our code is written, now if we ever get to the destination, oh, but we only go to places that haven't been visited. Okay, that explains this. Okay, so what happened here? Note that, so we only go to destinations that haven't been visited. This was here in our shortest path, same thing. If some place has been visited, we don't go there. And right now, we're setting visited to be true, but we're never clearing it out. And that has a problem for us. The problem is that the first path I checked was from 0 to 1, 1 to 2, and 2 to 3. And along that path it set this to true, this to true, this to true, and this to true. When the recursive method pops back out, and then it goes to try from 1 to 3, which would be a shorter path, it sees that 3 has already been visited because we never cleared that out, and it doesn't even try that option. And then of course when it pops back all the way out to here, and it takes what should be the shortest path, 2 has already been visited, and so it can't deal with that either. The way that we have to fix this is to do what I refer to as picking up the breadcrumbs. Okay, so in the previous video we talked about how this was laying behind breadcrumbs so it would know where it had been. In this case we need to sweep them back up when we are done, and This is, given the way that I've written this right now, this is a bit more challenging with this array of booleans, but I can do this much more nicely if instead of passing an array of booleans, I make visited be perhaps a set of booleans, and then a set of ints, so that every value either is in the set or it isn't, and then visited becomes, I want visited plus cur. I could actually, to save myself some work here, new visited equals visited plus cur, and then utilize that variable there. And so this is, because this value, it's an immutable set, and because it gets passed through into here, every time I call the function, I'm giving it this revised set of visited. When it returns back out, it forgets that this had been added to it and goes back to the earlier version of the set. And so this, now we're going to pass it the empty set to start with. If I run this, we get the value of 8, which is the correct value for this graph. So this is a method calculating shortest path. It does this actually by taking every single possible path through the graph and then returning to us the one that is shortest. And we saw how for this we have to be able to clean up our breadcrumbs. And in this case, one way of doing that is to pass in an immutable set, and so the immutable set gets modified as we push down into the call stack, but the values are basically cleared out when we pop back up. That's it for this video, and we'll come back next time and we'll look at a different application of recursion that winds up being kind of significant for a number of the projects that are suggested.